Hi, everyone. We're going to do section 2.4 today. It's the last section in chapter 2, which means that, tests coming here in our near future, probably next week at some point, we'll have at least a review day and then a test. Certainly, we're able to get through this lesson in totality today. That's what we're looking at for next week. Reminder on the tests, what you get to use on every test, half sheet of notes. You get to make yourself on the review day and turn it to me on the review day. I'll hold that note card for you. Give it back to you on the test day that you can use. Put anything you want on it. You can just go from front to back. Whatever you'd like to put on there. So just, if you, again, as you're doing homework over the weekend, if you decide that, hey, might be a good idea, this is something I've had to look up 3 times, maybe I start making my note card now, so that I have it ready as I'm doing things. Or not, whatever is kind of your process. I'm not going to micromanage you, just kind of talking. So this is the big, I've been hinting at this for a couple of days now. This is the big reveal here. So in this chapter 2, we started with this idea of SOHCAHTOA. It was our definition for sine, cosine, and tangent, where we're stuck inside of a right triangle using angles between 0 and 90 degrees. Today, we're going to break free of those shackles, and by the end of today, we'll have a definition for sine, cosine, and tangent that will allow us to take sine, cosine, tangent, and consequently secant, cosecant, cotangent of angles of any size. That's the point of what we're doing today. So the big piece that we accomplished last time was we defined angles of any size. Remember, we talked about the standard position angle where we set the vertex to the origin of the xy axis. We fix one arm that we called the initial side onto the positive x-axis, and then we rotated around that origin either clockwise or counterclockwise, depending if we're talking about positive or negative, whatever number of degrees, and then that was how we drew our angles, right? So we're going to start kind of from there, and our goal here is going to be creating a definition for sine, cosine, and tangent that's not into a right triangle. So this first version of this that we're going to do is we're going to translate our definition of SOHCAHTOA and turn that into a definition involving the point, any point on that terminal side of our standard position angle. So remember, when we talk about our standard position angle, we have the initial side that's fixed on the positive x-axis. And we have the terminal side on the other arm of our angle, right? So if I take any point on that terminal side, I'm going to just call that point P, and I'm going to say its coordinate is xy, because I'm going to do this generally. If I draw a line back down to the x-axis, I've just created a right triangle. Everybody agree with that? Okay, this angle inside that right triangle that we've drawn is called a reference angle. And this triangle is called a reference triangle. If I look at the side lengths of this triangle, this side has to be x long, because to plot the point xy, I go x over and then y up. Ooh, excuse me. Thank you. So remember, to plot a point, I go like x units over and then y units up. So if this is the point xy, that side is x long, and that side is y long. Everybody feel good there? That means that the hypotenuse then has to be the square root of x squared plus y squared. Just because of the Pythagorean theorem, right? Now, that stinks, so we're just going to call that r. And just agree that r is equal to the square root of x squared plus y squared. So now if I take SOHCAHTOA, and I use this angle alpha here, opposite is y, hypotenuse is r, so I'm left with y over r. Notice I've taken SOHCAHTOA and translated into the y-coordinate on this point on the terminal side, and the distance that point on the terminal side is from the origin. So I've now broken away from needing to use SOHCAHTOA. Now all I need is a point on the terminal side, and I'm able to accomplish the same thing. Similarly, if we go to cosine, that's adjacent over hypotenuse. So in our drawing, adjacent is x, hypotenuse is r, so x over r. Does everybody feel okay buzzing through this, see where everything else is going to land? So in general, what we have here is SOHCAHTOA, where opposite is y, hypotenuse is r, and adjacent is x. We've just translated SOHCAHTOA onto our standard position angle using any point on the terminal side as like my codex to make that translation. Like my Rosetta Stone. You know what the Rosetta Stone is? It was a really important archaeological find. They found like ancient Egypt. It was a rock that had the same the same story on each side. One was in Greek, one was in hieroglyphics, one was in, I don't know, another language, but it was like how they figured out how to read hieroglyphics. Because they couldn't figure it out because it's all pictorial. Couldn't figure out how to do it. So they found that inscription had the same thing written in like a couple of different languages. And they're like, aha! That's what I used to make my translation. That's essentially what we're doing. We're using SOHCAHTOA to make a translation. Is everybody okay with that? Those definitions there, the point on a terminal side definition for sine, cosine, and tangent, that's something that I would probably want to include on my note card for the test. Now, if you're like Mr. Kulik, I'm just going to memorize that O is Y, H is R, and A is X. And like I don't have to write things like, that's cool, that's great. I applaud you for doing so. That's a great way to simplify your memorization, is to just be like, I know SOHCAHTOA already. I'm just going to remember like how to translate that into points. Cool, that works for you, that's great. I mean, that's the way I did it. But like, this is something that I would want the formulas written down, right? So let's do an example. So it says the point, negative 3, 4, lies on the terminal side of angle theta. Find the values of all 6 trigonometric ratios for angle theta. So again, to do that, I'm just using these values for those formulas. What I'm given here is an x and a y. What I don't have given to me is r in my formula, right? I have r's in a lot of those formulas. You can find that r. Do you remember what r was? We wrote it down in the previous picture. X squared plus y squared all square rooted, right? And then fill it in. If you have your calculator with you, do that for me. -3 squared plus 4 squared all square rooted. This is just me to show you if you're having trouble getting something into your calculator, which I think is often the case in this situation. Best we address it right now. Did anybody get an error when they attempted to do this? That's good. How many of us got 5 as our answer? How many of us got a number other than 5 for our result? So the reason 5 is the answer, the reason you would have gotten something other than 5 is you wrote -3 squared into your calculator. The calculator is going to follow the order of operations and square it first and then make it negative. What you really meant was make the number negative first and then square it. So you have -3 times -3. So you have to type it in with the parenthesis.
I did that in still show.
Oh, it's because you are outside, the plus was outside the square.
That makes sense.
So just, you pressed over, I think, one too many times or something, and you got outside the square. So this mistake, I see students, especially at this level, make frequently when using their calculator. You're going to square a negative number, you need to use a parenthesis. Yes. So your issue is that there's a built-in parenthesis here. So it's just the square root of -3 and squaring it. So you need the square root parentheses to start and then a parenthesis around the -3. Does that make sense? You just have like the older operating system. So like if I look at newer operating system, like it puts the square root in there, so it's like what you write on your paper. So upgrade your calculator, you'll get that new operating system. It makes it a little bit easier to tell what you're typing in. But if you're using the older calculator, that's so just whatever you have to do. That's the calculator you're using. Yeah, of course. And again, I'm happy to help. Okay. So we have X, we have Y, we have R. All we're doing now is filling in our formulas, right? Who can tell me what sine theta will be? 4 over 5.
Oh,
Remember, the R is 5. This is just me showing an example of like oopsie on your calculator. This is like an aside, right? Not part of the calculation. And cosine theta then, what's that? -3/5, very good. And tangent theta is? 4/-3. And does it matter where I put that negative sign when I write a fraction like that? Remember, this is still the same thing as this, or the same thing as this, right? Those all mean the same thing, okay? Does it matter to me which way you write it? Nope. Everybody good? Okay. Cosecant theta then will be 5/4. And secant theta will be 5/3. Good. And cotangent theta will be no big deal on this, right? You just got to recognize that I need this other formula or set of formulas, but like the calculation to get the pieces you need, it's a Pythagorean theorem. And then just plug in things in. What's the worst case scenario? You might have to rationalize a denominator or something, because there might be a radical in it. Like the arithmetic could get messy, but like the concept, it's like they're all the same. Pausing here, how do we feel on this? Is this okay? It's basically just still SOHCAHTOA, but now we can do it for like, 190-degree angle, where we couldn't do that before if it had to be part of a right triangle. So the next thing we want to do is predict where sine, cosine, and tangent are negative. That's a less than 0 there. So if I think about that, in quadrant 1, the x-coordinate's always positive, the y-coordinate's always positive, and the r is a distance. And distances are always positive, or a length, I should say, maybe rather than distance. So all of our trig functions will be positive in the first quadrant, or when the terminal side ends in the first quadrant, I should say. Is that okay? In the second quadrant, the x-coordinate is negative, because now we're going left, but we're going up, so the y-coordinate is positive, and our r is always positive, because it's a length. So if I go back and I look at my formulas, any of these that have a y in it are going to be negative, right? So we have sine is less than 0, cosine, sine is greater than 0, cosine is less than 0, and tangent is less than 0, because all of them have an x in their formula. Yes? Sure. Everybody feel okay? In quadrant 3, x is negative, y is negative, but that r is always positive. So any of my trig functions that have just one x or just one y will be negative. But if they have both, negative and negative, like negative over negative makes a positive, right? So sine is negative. Cosine is negative, but tangent, y over x, that'll be positive. And then quadrant 4, my x is positive, my y is negative, the r always positive. So here, anything with a y in it is going to be negative. So that's going to be sine and tangent, but cosine is going to be positive. This turns out to be a really important piece of information to remember. So the way that when I was a student, a math student, the way that I was taught was through like an acronym where we used the first letter of the trig function that was positive in the quadrant. So we did A for all, S for sine, T for tangent, and C for cosine. And what we said was all silly turtles crawl. I don't know why, but I still remember it 40 years later or whatever. So it couldn't have been that bad of an idea. But all that is like an acronym to remember which trig function is positive in that quadrant. So S for silly tells us sine is positive, and it's reciprocal, so cosecant, but everything else is negative. T, turtle, T, tangent is positive, and it's reciprocal. Everything else is negative. Crawl, C, cosine. Cosine is positive, and it's reciprocal, secant. Everything else is negative. So that's how we use that piece of information. Is everybody okay with how we built that out? And at least the acronym that I used to memorize this when I was a student? You can come up with your own words if you want. You know, all students, you know, do something. TC, whatever. Take calculus. They don't. Everybody's so far okay? Again, this will come up again and again and again all through first semester. So like, you need to be able to use this. Do you actually have to memorize it? Not for a test setting, because what can you always do? Put it on your notes, right? So you don't have to memorize it, but you do have to be able to use it and make sure you're able to use it. Also, turtles crawl. All right. So here we're going to ask us to find cosine of 150 degrees. This was something we could not do with SOHCAHTOA because this is an obtuse angle. So the way we would start is by drawing our XY axis, because I'm going to graph 150 degrees as a standard position angle. So I place the vertex of my angle at the origin. I draw the initial side on the positive x-axis, and then I rotate the terminal side counterclockwise. So I go 90 degrees and then like 60 more. And that's 150 total. Does everybody feel okay so far? Okay. Now I'm going to build my reference triangle just like I did before in the example where I derived those shortcuts. So I'm going to pick some point on the terminal side, it doesn't matter where, and I'm going to draw a line down to the x-axis. Always to the x-axis. So that makes my reference triangle. Is everybody okay? What is this missing angle down here got to be for this reference triangle? 30. How'd you get that? Because the quadrant has to add to 90. We already did 60 in, so this piece has to be 30. If that angle's 90, what does this upper angle have to be then?
60.
60. So what kind of triangle do we have? That special 30, 60, 90 triangle. Everybody's okay with that? Yes, Lily?
Can I go over that?
Mm-hmm. So remember, the side lengths of this 30, 60, 90, and 45, 45, 90 triangle exist in specific ratios. So remember, we said that the short side of our triangle, called A, the middle side is going to be the square root of 3 times A, and the long side is 2A. Everybody okay so far? What quadrant is that terminal side in, though? It's in the second quadrant, right? If we remember up above, the x coordinate is negative in the second quadrant. Everybody's good? So when I do this, the side on the x-axis is going to have a negative value, so that this point here becomes negative a root 3, comma a. Because I've gone x over to the left, and then like a up. Yes,
Where
Addie.
do you get the 2A and the square?
So that's something that we learned in geometry. That's our definition for a 30, 60, 90 triangle. Those ratios of side lengths were something we defined in geometry. Maybe even you derived them using the Pythagorean theorem, but I probably think not. Probably just was stated, and that's all I'm doing now is stating them. But that's always the case for all 30, 60, 90 triangles. That's like a fact. And a good one to maybe put on a note card. Along with the 45, 45, 90 triangle. And if you don't remember those, we had those in, I wrote those out also in the 2 notes here somewhere, I think.
Okay.
So they also appear here. Okay. So, cosine theta is x over r. So if I look at this, I have x, I have y, and then I have r in my picture. So it just is negative a root 3 over 2a. Which reduces down to negative root 3 over 2. If you have a calculator with you, do me a favor. Take it out, type in cosine of 150, press enter, and then type in negative square root 3 divided by 2 and press enter, and just confirm that you get the same decimal for each one. Should be 0.866 and change. Or negative 0.866 and change, excuse me. So that's a perfectly reasonable way to check your work, even if we're asking for an exact answer. You can type in cosine 150 into your calculator, get the decimal, take your exact answer, get the decimal, and make sure they're the same. If they don't match, either you've made a mistake in your calculation, could be, type something into your calculator wrong, possibly. You're in the wrong mode on your calculator, often very likely. If things are like, I think I did that right, why isn't that working? What mode would our calculator have had to be in for this problem? Degree. Because the angle's in degrees. Does everybody feel pretty good to this point? Again, not super hard what we're doing, but it's really, from here on out, like what we're doing here today is like every day. So like if you can't do this, it becomes a problem and builds and builds and builds, and eventually like the whole thing is a mess because you don't understand this one foundational part. So I'm really trying to go slow and be careful here and really hammer it. Notice I did not blaze through chapter 2 at all. We've like settled in and really made sure we remembered SOHCAHTOA and like wanted to move from a foundation where everybody was kind of at the same spot. Okay, so this is real close to our finishing point, but we can do a little bit better than this. Okay, the place where we had some choice is we just chose to pick this P to be at any spot on the terminal side, right? It works wherever you pick it. What we're going to do is we're going to standardize how we pick that P every time, and then look at the result because it simplifies everything down just a little bit more. Okay, so this is a transitionary step to getting to what we're really going to want to use. Everybody's good? Okay. The way we do that, we're going to standardize our choice of P so that the distance from P to the origin is always 1 unit. Okay, always 1 unit. If I do that, where we do one of these things, I pick my point P, some x comma y, and if that's 1 unit from the origin, the r is 1. So all of my old formulas collapse down if I just replace my r's with 1s. Notice that y over 1 and x over 1 we just write as x and y. Sure. So if I look at the set of all these points that are 1 unit from the origin, what shape am I going to be making? A circle. And if all those, every point on that circle is has 1 unit from the origin, the radius for the circle is 1 as well, right? Since the radius is 1 unit, we're going to refer to that as a unit circle. So far, so good. I want to And yes, sure. So what we're going to do with that unit circle is we're going to go and figure out all the values for sine and cosine, for all the xy's that correspond to angles whose reference angle is either 30, 45, or 60 degree or multiple thereof. That is what this picture is illustrating. So if we take a look at this, and I just say, for example, we had like our initial side, and then we had a 45-degree angle. And we did like, okay, built this down. So this is and A root 2. And this coordinate would be, well, if we standardize this to 1, oh, come on now. That means that A would have to be 1 over root 2. So this point is like 1 over root 2 comma 1 over root 2. And when we rationalize the denominator, we get root 2 over 2. So all this picture is saving us the work of drawing these reference triangles and using our ratios of side lengths from 30, 60, 90, and 45, 45, 90 triangles to figure out what the xy would be at that point. It is essentially taking like all the work we did to get this and just saving us from having to do the work every time we run into one of these guys. Because notice, if I look at 150 degrees, we said cosine was x. So if I go to my unit circle and I look at the x coordinate, cosine should be negative root 3 over 2. It's exactly what we saw in that previous example. And look at how fast that happened. All I had to do was look it up off a sheet of paper. That's what this is doing. This is a fancy exact value calculator for you, where it allows me to do sine, cosine, tangent, cosecant, secant, cotangent of angles who are multiples of 30, 60, or 45 degrees and get an exact answer without having to draw any pictures and like build any coordinates. I just have to be able to read it off this. Okay.
Would that be good to put on
This would be given to you on any test you take.
Oh, it is?
Yes.
Oh,
I would not make you copy this.
okay.
I would not make you memorize this.
I have a meeting with Mr. White.
Sure. Say hi. Okay. From me, though. Not, you should say hi to him also, but like that would be rude to just walk in and be like, hey, what's going on? It's our meeting. Yes. Of course. Okay. And we'll do a delta math maybe next time on the review day, just to practice you reading off of this thing. But it'll be part of the homework as well. Just like, you know, if I want to do tangent of 210, you know, I locate 210. I look up my formula. Tangent is y over x. So I'm going to write 1 negative 1/2 over negative root 3 over 2. Everybody's okay? Negative signs cancel. They're both over 2. Those cancel. I'm left with 1 over root 3. I rationalize the denominator, and there's my exact answer. Notice I didn't have to draw any pictures. I did not have to use the Pythagorean theorem. I did not have to do any fancy geometry. I just had to read the numbers I needed off of the picture and plug them into a formula, and I'm done. So this unit circle, the way to think about this is an exact value calculator. Because the calculators you have, you type in cosine of 150, it cannot give you negative root 3 over 2. Cannot give you the exact answer. And from the decimal, there's no way to recover the exact answer from it. But this thing will do it. You just have to know how to use it. That's all this is. You guys feel okay? We'll practice using this more next time. I think I have one more example in here to do. It says to find sine theta if cosine theta is 5 over 7 and cotangent theta is less than 0. So this is a problem that I would do as a point on the terminal side definition. This is one where I would use the R definitions for sine, cosine, and tangent rather than the unit circle definition. So what I'm looking at is I would start here. 5 over 7 is a positive number, right? Cotangent is negative, and that means that tangent should also be negative. I'm going to go now to my all silly turtles crawl picture and look for the quadrant where cosine is positive and tangent is negative. So if I go back up here, cosine positive, tangent negative. My location should be in quadrant 4. Everybody happy with that? So if I draw my standard position angle, should look like that, right? Everybody still good? I'll draw my point on there. I know my x is going to be a positive value, and the y is going to be a negative value. Because I'm in quadrant 4. So far, so good? Now, I remember that cosine theta is x over r. And if cosine theta is 5 over 7, well, x is just 5, and r is just 7, right? So I know the x-coordinate at P is 5. The y-coordinate, how am I going to find that? Pythagorean theorem. Because remember that x squared plus y squared is equal to r squared. 5 squared is 25. 7 squared is 49. 25 minus 49 is 24. And if we square root both sides, we get plus or minus the square root of 24. Here, remember, y is no longer a length. Y is a coordinate. So both positive and negatives are viable because y is a coordinate, right? In fact, we know whether y should be positive or negative already. We've already noted it. We said y had to be negative because we existed in the fourth quadrant. So here, we're going to lose the positive from my plus or minus. Most common mistake students make on this problem is not knowing what to do with the plus or minus. And the way you're going to know is in the very beginning when you draw your standard position angle, making sure you get it in the right quadrant. It all comes back to all silly turtles crawl. Okay? So one last thing I need to do is to reduce this radical, right? Hopefully you see the square root of 24 can be the square root of 4 times the square root of 6. So we'll just make that negative 2 root 6. So we have x, we have y, and we have r. I can now give you any trig function that you want, right? I think this question asks for sine, though. So sine theta equals y over r. And I'm done. The hardest part about this type of problem is making sure you draw the correct picture. You can draw the correct picture, usually everything is downhill from there. It's typically pretty easy. And you're going to find that over and over and over in the trigonometry portion of this class. If you can draw the picture well, everything flows pretty nicely from there. If you struggle to get that terminal side in the right quadrant, over and over and over, it's going to cause problems. So I cannot emphasize how important the all silly turtles crawl piece is to making sure you're consistently getting those terminal sides in the right places. It matters so much. This is my stopping point. So at this point, you can now do the rest of the problems, 45 through 60. Now, when is that going to be due? That will not be part of this Sunday's problem set because I'd like to have a regular class day in which you can ask questions if you're stuck on stuff. So that'll be part of the following Sunday's problem set. Carol? Sure.
That should be 2, should be 3, should be 4.
So these are this Sunday's problem set is this set of 3 things. The following Sundays will be this set of 3 things. Obviously, I haven't assigned another Delta Math yet. We just had the 2 that we've assigned so far. I don't think I've made the 3rd Delta Math yet. And we haven't assigned the review yet. There'll be a day, the review day in class, where you can work on the review and work on your note card. So don't worry about that yet. The 45 through 60, not due yet. You notice on the OneNote, the review's already posted. If you're like, I want to get an early jump on things, if you're telling me the test is going to be sometime next week, like, I respect that. No problem. The review is there for you, as well as the answer key for the review, so you're able to check as you go. Now, I will expect that you have a review of your own turned into OneNote still, even though the answer key is posted. It's mostly posted there so you can check as you go and get feedback. Because the last thing you want is like doing the review and doing things wrong and not realizing it until it's too late. Since we won't take a day to formally go through the review, I'm just going to post a key, let you guys work on things. And if you come back and want to ask questions about it, I'm happy to take questions, but all the solutions for that are there. You guys feel pretty good about what's going on?
You said that problems 43 and 60 are due the following Sunday.
45 through 60, I think. Is my minor name messed up? I'll probably
It says it's due in 3 days.
through 60?
Yeah.
Okay. Oh, thank you. Appreciate that. Again, I have to make these things, and they all have to have due dates attached to it. Just like, I wish I could just do a sign date. Is this day, and like we'll figure out the due date later. But I usually go with, I'll assign it earlier, maybe, like when I have to pick a due date, I'll usually pick something earlier than I actually think I can get to, because nobody gets mad if I extend due dates. But if I'm like, oh, that thing that I said was due in 2 weeks is actually due in 1 week, everybody has a fit, right? Which is understandable. Like when you get good news, like, oh, that's due later, nobody's mad about good news. If you get bad news, like that's due sooner than you thought, everybody gets upset. So in general, you're like, that feels like it's not going to be due yet. You could be right. And like the due date just gets pushed out because I'm forced to pick due dates. And you just operate on like, how are we doing? What did I get through? How did things go? You know, just do the best of that. But as we've established, homework due date, how big of a deal is it to me? Not big, right? Because everybody gets a week of grace on all your homeworks. So if like something gets miscommunicated or like you misunderstand or whatever, if something gets marked missing when it's due, is it a big deal? Not really, because you have a week to kind of get that straightened out, caught up on. So again, like I'm not going to stress out about it. You shouldn't stress out about it too bad. Like obviously, yes, try to have things done on time. That's for the best. But if you don't, if something gets lost or miscommunicated or you have a technology issue or something doesn't sync right or whatever, there's no reason to panic, right? Even the homework quizzes, like don't panic. It's okay. And how did you guys feel about the homework quizzes?
It wasn't too bad. I didn't know how to do the angles for the first question.
Oh, the first question, all you do is plug into the formula.
I think I did it right.
Okay. You should just plug into the formula and then maybe like might have to solve, like divide
wait, I
something to
did
both
that.
sides. Like that's it. There's nothing more to it.
Oh, that's all I did.
It should have been like, whoo, okay.
I think the last one I was
Last one was just like a SOHCAHTOA, like right triangle problem.
were the answers in decimal?
Yeah. Yeah, I think the direction said to round to like 2 decimal places or something.
Yeah, I didn't know how to do those ones.
You should have gotten decimals. That was okay. Just using SOHCAHTOA.
So
I did, but
Okay.
on the test two info,
Uh-huh.
and when it says to solve for argument 3 as your central table, is that like what the first question was?
Yes. If you're just using that formula where you're given 2 of the 3 and you have to solve it. Yes.
grades.
Exactly right. The only catch with that is you gotta make sure you pick the right formula, because you have one that's good for radians, one that's good for degrees. So that's the only catch. You gotta make sure you're doing the right formula.
Wait, what's the other one? It says that S equals R.
R theta, that's the radian version. And the degree one is S equals R theta pi over 180.
No, I don't do that.
So it's just like, the hardest part is making sure you fit it right.
Yeah.
You know?
And so then if the question was like, how would you know which one to pick?
Well, the angle will be, the angle that's given to the theta, you measure it in degrees or radians.
Oh, okay.
And then just whatever information you're given, you pick the one that matches with it.
Okay, that makes sense.
I know.
And he's a wrinkle on his face.
I know.
He's chopped.
So in general, folks, are you getting like, you feel like you're getting enough advance warning on when stuff is coming?
Yeah.
Like I try to have all this stuff up so you can see what's gonna be happening, what's gonna be due, like the notes that we're gonna use, like the scaffold that I'm gonna fill in. I try to be really transparent on that stuff, so it's like not mysteries. You know, like the reviews there for review at like the start of the chapter, so that if you wanted to like, you know, if you have a tutor or whatever and you wanna show them what you're doing, like you can just show them the review, be like, this is what we're doing this chapter. You know, and then be like, okay, we're not done with it, we're just starting, but like this is the review. Oh, helpful. So that's it for me. You guys feel okay?
Yeah, I'm hungry.
Not too scared yet? Okay, how am I doing on my promise of being nice? It's been pretty nice.
Yeah.
That's really nice, yeah.
Yeah, like I try real hard. I know that math is oftentimes the scariest of our subjects. I don't need to contribute to the scariness there. So.
I'm hungry.
I'm hungry and I'm bad.
Abby, you can't.